All right, taking a look today, we're looking at 7.5 properties of logarithms. We've kind of established by the definition what is a logarithm, how to evaluate, basically simple expressions and just kind of an introduction. Now we're going to look at properties of logarithms, very similar, or a lot of these are very similar to our properties of exponents as we go through things. All right, so our first property is going to be looking at the product property of logarithms. It's kind of related to this idea. So when we have 2 times 3 and 2 times 4, or 2 to the third times 2 to the fourth, rather, sorry. When we multiply powers, we add exponents, okay? So when we're talking about logarithms, note it's the same idea. When I have a log of a product, I can add the logs separately, okay? And this is probably going to be the most confusing part, is coming up with numbers that work to satisfy the numbers you're given. Okay. All right. So typically what happens is we're kind of working into how to use our calculator. Okay. And we're not quite there yet. So what we're going to do is we're going to give you decimal approximations. Okay. So log base 4 of 3 is 0.7925, which makes sense because log base 4 of 4 would be 1. So it makes sense that it would be less than 1. Implied with these, like I just said, log base 4 of 4 is 1. All right, 4 to the first power is 4. And log base 4 of 1 is 0. So even though these aren't written, you always want to think of these two implied expressions, because these could help you come up with the product. All right. In this instance, we're just looking at the product. Okay. So I'm thinking of how can I use a 3, a 4, and a 1 to create 12? Well, easy enough, right? 12 is 3 times 4. Okay. So I have a log of a product. All right. At this point, the log of the product is going to be same thing, or the same thing as logging each number separately and adding them together. All right. At this point, then we can substitute in values. Log base 4 of 3 is given to us in the problem. It's about 7925. Log base 4 of 4 is 1. So my answer is 1.7925. Or 4 to the 1.7925 is about 12. And if you typed 4 to the 1.7925 in your calculator, you would get roughly 12. Okay. Keep in mind, you're not going to get exactly 12 because this is a decimal approximation. Okay. Let's do the same thing on the next question. So I am trying to come up with a product of numbers that gives me 192. Okay. So I'm thinking 192, 192, 192. All 192 is 64 times 3, which is 4 times 4 times 4 times 3, correct? All right, so keep in mind our products don't just have to be 2 numbers, they can be multiple numbers, okay? So this is the log of 4 times 4 times 4 times 3. And then, like we said, if we have the log of a product, we can log each separately. Log base 4 of 3 and add those logs together. So we have 1 plus 1 plus 1 plus 0.7925, which is 3.7925. All right. Yay! So that's the product property of logarithms. Next property we're going to explore, quotient property. All right. Really similar to the idea of where we have 2 to the 8th over 2 to the 5th is 2 to the 3rd. Right? When we have powers, we subtract their exponents. Same is true with quotient of, or log of a quotient. Okay. So what I can do is log each separately and then subtract. All right. For this situation, we're going to kind of use this slightly more real world application. So We're in a room. The loudness of a person talking can be denoted by this equation 10 log base 10 of R, okay, where R is the sound's relative intensity. Suppose one person talks with a relative intensity of 10 to the 6th, or what's known as 60 decibels. How much louder would 100 people be? Well, you'd think 100 times, right? That's kind of what intuition says. If one person talks 60 decibels, then 100 people will talk 160 decibels, right? Louder, or 160 times louder, or 100 times louder. I apologize. All right. Well, let's figure this out. All right. So we know the loudness is looking at 10. 10 log, not log 10. And I did the exact same thing. 10 log, and then even though the base isn't there, we're assuming it's base 10. All right. How much louder is 100 people talking at 10 to the 6th versus 10 to the 6th? Okay. And the reason we're comparing these numbers is we're looking at the sound's relative intensity. So we have 100 people talking at 10 to the 6th, or we have one person talking at 10 to the 6th. Okay. So we're going to use our properties to kind of come up with this idea. All right. So looking here, we have 10. I'm gonna quit because that's the third time I've done that. Right? So we have 10 log base 10, and then keep in mind here we have 100. Sorry, looking ahead. This is 10 to the second, correct? All right, 100 is 10 to the second. So up top we have 10 to the 8th. I'm just going to put that in there. And we have log base 10 of 10 to the 6th, correct? And then what we're doing is we're subtracting those each. All right. So we're trying to figure out how these numbers relate. All right. So we have 10 to the 8th, 10 to the 6th. We're subtracting those logs using that property from above. I don't know why the keyboard just showed up. Okay. Well, thinking about this question, log base 10 of 10 to the 8th, or 10 to what power is 10 to the 8th? Hopefully that's pretty easy to see. It's going to be 8. Log base 10 of 10 to the 6th, 10 to what power is 10 to the 6th? Well, again, pretty straightforward. It's 6. So what's 8 minus 6? 2. 2 times the original 10 on the front is 20. All right. So kind of counterintuitive. All right. If we have one person talking at 60 decibels, we have 100 people talking at the same volume. It's only 20 times louder. It's not 100 times louder. All right. It's kind of an interesting fact there. All right. Continuing on to our last property is the power property. All right. Thinking about power property, very similar to, or actually, sorry, not similar to, but actually related to kind of this last idea we just did. All right. Log base 10 of 10 to the 8th, that's 8. Log base 10 of 10 to the 6th is 6. Okay. In essence, what we can do is if we have a log of a power, the power can drop right out front of the log, and it's the same thing. Okay. So thinking about that, if we went back here, if I took the 6 and I dropped it out front, log base 10 of 10, remember, is just 1. Right? So this whole thing is 1. 6 times 1 is 6. We can use that power property as well. All right. So we're going to get back into those approximation models. Let me leave that up there for you. Okay. So we have log base 2 of 5. Keep in mind, we always have the 2 implied. So log base 2 of 2 is 1. We have log base 2 of 1, which is 0. Okay. So always keep those in mind. We're never going to write those down because those are kind of givens. We don't need to state them. You should already know them. So the question is, how can I use powers here? Well, I know 25 is 5 squared. All right. So if you can remember back, that power can drop out front. So then we have 2 times log base 2 of 5. we can substitute in our approximation. So we have 2.3219, which means we wind up with 4.6438. All right, kind of doing the same thing on the next question. We have 3 log base 2, 125. All right, I know that 125 is 5 to the third, so I'm going to swap that in. All right, now I can use my power property. I know that this power can come out front. There's a 3 already there, so 3 times 3 is 9. And then we have log base 2 of 5. Log base 2 of 5 is that approximation that's given to us before, so we have 9 times 2.3219. All we have to do is multiply that out, and we get 20.8917. There we go. So those are the 3 properties. When we're logging a product, we add. When we're logging a quotient, we subtract. And we're logging a power, the power can come out front. All right, the last thing we're going to kind of explore today is how those rules and properties are helpful in terms of solving. And I'm looking here and I noticed for whatever reason, the problems have disappeared. So here we go. We had 2 log base 7 of x equals log base 7 of 27 plus log base 7 of 3. All right. So today we're going to use our properties to solve equations. Okay. So these are going to be a little more tricky than a couple days ago when we were solving basic logarithms. Today we're going to want to use our properties. Okay. Because remember, when we have multiple logarithms, we want to get them on different sides. And then whatever we're logging, we can set equal to each other. Okay. But it would have to be a single log on each side. Okay. With that being said, if I want to create a single logarithm on this side, remember when we're adding logs, it's the same as the product of the 2. So 3 times 7, or 27 times 3 is 81. So I can use that property in reverse. Okay. If you think back to before, we took a number and then we broke it up into a product of 2 separate logs, right? Now we're kind of using that property backwards. So if I see the sum of 2 logs, I'm going to multiply, all right? If I see a number out front, remember that's a power. So I can change this into log base 7 of x squared. Now I have 2 logs completely isolated on the one sides. So I know what I'm logging must be the same. So then we know that x equals plus or minus 9. We want to plug back in our answers to check. Always go back to the original to check. You will notice that we cannot do 2 times log base 7 of negative 9. So my only answer is 9. Okay. Remember to always go back to the original equation to check. All right. Next problem, we have log base 6 of x plus log base 6 of x plus 5 equals 2. For whatever reason, these tend to confuse people. Please don't let it confuse you, okay? We have a sum of 2 logs. So you're hopefully thinking to yourself, well, I need to multiply those together, which is perfect, okay? Now, a lot of the problems we've done have 2 logs on separate sides of the equation. This one only has a single log, okay? This problem is actually really easy, all right? For whatever reason, people just like to say that x squared plus 5x equals 2. That's not the case. There's no logarithm on this side, okay? We can't do that, right? What we have to do is use that definition. Remember, logarithms, base, power. So 6 squared equals x squared plus 5x. And then we can move the 36 over and solve this way. So we have x plus 9, x minus 4. We get our 2 answers. When we go back to the original to check, We can't plug in a negative. So the only answer that works is positive 4. Okay? Be super mindful on this question. These types of questions are almost always missed on the quiz and test. Okay? When you have a single logarithm, we use that definition. 6 squared equals x squared plus 5. Okay? And I guarantee you probably 25% of people are going to screw it up on a quiz. And they're just going to say x squared plus 5x equals 2. And then they're not going to get nice answers. Okay? If you do this correctly, you will get nice answers in the factored expression. All right? So that's 7.5. Assignments on the bottom of the page. Make sure you do the book and the worksheet. If you have any questions, feel free to reach out via the discussion board, live feed, or in class. Other than that, enjoy